Good morning. I'm Lim Wenxuan speaking with Evan Lim Hongyan, Vishal Analaki Kumar, and Ong Hui Chun. Our project Urban Earth Intelligent Data-Driven Pathways to Resilient Healthy City uses NASA Earth observation and allied dataset to help city prioritize action that protect human well-being and ecosystem while guiding sustainable growth. Our approach combined comparative analysis across a 124 city sample concentrated in Southeast Asia and Malaysia with a prototype decision support dashboard for planners. We compute indicators such as population-weighted heat exposure, green space per capita, and groundwater stress to identify priority intervention zones, typically where high heat, low green space, and dense population overlap. Our deliverable include an MVP dashboard for pilot deployment. The project is organized into four analytical modules, which include urban form and mobility, geologic and climatic hazards, geology and water security, and well-being environmental correlations. We draw on satellite sources including Landsat, MODIS, Sentinels, and GRACE, settlement layers such as UHSL and WorldPop, and socio-economic data set from SEDEC and national statistics. Indicators are computed, population weighted, and combined with uncertainty flags to produce robust, actionable maps. Module 1 quantifies build form, road network morphology, and transit access. Cross-city analysis show that sprawl correlates with higher transport emission and reduced green space in roughly 78% of sample cities. Cul-de-sac dominated suburbs often experience 2 to 3 times longer travel time to basic services. Intervention here focus on transit-oriented infill, connectivity, retrofit, and green corridor creation to reduce heat and improve access.
Module 2 maps hazards, which include seismic exposure, subsidence measured by INSA, coastal vulnerability, and a multi-hazard composite score. Key findings identify low-lying deltas and peri-urban fringes as hotspots, where subsidence often co-occurs with groundwater depletion. Recommended engineering and planning mitigations include managed aquifer recharge, targeted levies, nature-based coastal defenses, and hazard-informed seating of critical infrastructure. Module 3 assesses water security using GRACE, aquifer, trends, surface water extent, time series, impervious surface grow, and watershed health proxies. Several sample cities show statistically significant aquifer decline and surface water contraction, increasing flood and supplies risk. Priority actions include managed recharge, leakage reduction, watershed protection, and retention basins to restore hydrologic resilience.
Module 4 links environmental exposure to well-being outcomes. We find consistent negative correlations between population-weighted LST anomalies, pollution indicators, and life expectancy or subjective well-being, and also positive correlations for green space and healthcare access. Heat waves and pollution produce measurable reductions in life expectancy and waste heat-related morbidity. Therefore, greening, cooling strategies, and improved service access are public health priorities.
We synthesize module outputs into a composite vulnerability index to identify areas where multiple stresses overlap. Strategic insight multi-sector place-based interventions in these zones yield larger aggregate health and ecological benefits than isolated projects. Policy design is guided by principles of equity, cost effectiveness, co-benefits, and transparency. The process follows evidence, prioritizations, pilot, evaluate, and scale.
Policy clusters span mobility and land use reform, nature-based solutions, water security, drainage, public health and pollution control, infrastructure resilience, and food or energy or waste systems. To operationalize these recommendations, we propose the Urban Earth Intelligence Dashboard, a map viewer, vulnerability engine, and scenario simulator that produces one-page diagnostics and supports what-if policy testing.
The MVP will be piloted in 10 representative cities over a 6 to 9 month timeline. Data ingestion, analytics, and UI build, then deployment and training. Technical architectures uses automated ingestion, containerized ETL, PostGIS storage, and an API layer for serving maps and exports. Success criteria include dashboard adoption by planners and initiation of at least 2 policy actions in pilot cities.
We acknowledge risks. Risks include data gaps, institutional resistance, privacy concerns, funding shortfalls, and technical debt. And proposed mitigations risks include data confidence threats, early co-design anonymization protocols, phased funding, and documented containerized pipelines for maintainability. Governance arrangements include DSAs with municipalities, tiered access, DPIAs, and a steering committee to ensure accountability. In closing, Urban Earth Intelligence translates Earth's observation into practical municipal tools that prioritize health, equity, and ecological integrity. Immediate next steps are confirmation of the 10 pilot cities, execution of data sharing agreements, and scheduling a first co-design workshop within 6 weeks. We welcome your questions and look forward to partnering with municipal teams to turn these technologies into measurable improvements on the ground. Thank you.